Hello, welcome back. Now we proceed with the next chapter, chapter 6, work power energy. Here we deal with work, energy and power. Work is defined as the scalar product of force and displacement, F dot S, Fs cos theta. Work is a scalar. Work can be negative if angle between force and displacement is an obtuse one. If angle is acute, that is positive, work is positive. Work can be zero. Even when force is not zero, displacement is not zero. That is only when the angle between force and displacement is a right angle. So force is perpendicular to displacement, work done is zero. If the point of application of the force does not move also, work is zero. If no force, no work. If there is force, there is displacement, also there is a chance of zero work. There it's possible if force is at right angles with displacement. Work is a scalar. Work and energy have same dimensions. Work done by a constant force, you can use this F dot S, Fs cos theta, because F is a constant. But if force is a variable one, we have to use the integral formula for doing work. Work done is equal to integral f of x dx, where work done by that force, and that force is a variable one. That force is variable over a position xi to xf. Integral xi to xf, f of x dx is the formula for work done by variable force. Now work energy theorem. Work energy theorem states that work done by net force is equal to change in kinetic energy. What is work energy theorem? Work done by net force is equal to final kinetic energy minus initial kinetic energy. Work energy theorems can be stated in other form. Work done by a conservative force. Work done by conservative force is negative of change of potential energy. That implies U initial minus U final. So W C means work done by conservative force appears as negative of change of potential energy. Work done by net force appears as final minus initial kinetic energy. Now if frictional forces are present, we can separately calculate work done by frictional forces. Frictional force is a non-conservative force. Work done by all non-conservative forces equal to change of mechanical energy. That means final mechanical energy minus initial mechanical energy. That means final mechanical energy is final kinetic energy plus final potential energy. Minus initial mechanical energy means initial kinetic energy plus initial potential energy. So work done by non-conservative forces equal to change of mechanical energy. Work done by net force appears as change of kinetic energy. Work done by conservative force appears as negative change of potential energy. All these work energy theorem statements are very important. So repeating, work done is the dot product of force and displacement. Work done is the dot product of force and displacement, that is W equals Fs cos theta. Theta 90 works 0. Theta 270 works 0. Whatever angle where force is perpendicular to displacement, work is 0. Theta obtuse work is negative. Theta acute work is positive. Graphically, how to explain this? If force is acting along this line and displacement is along this line, angle between these two is theta. Force is a vector along that line. Displacement is along this line. Drop a perpendicular from tip of force vector onto displacement vector to get the component of force vector along displacement. Now the component of the force vector along displacement is what? F cos theta. Then work is F cos theta into S. That is scalar product. F dot S Fs cos theta. Similarly, you can try dropping a perpendicular from tip of displacement vector onto force vector, so that this angle is 90 degree. Previously this angle was 90 degree. Now this is 90 degree, so that component of displacement along the force vector is S cos theta. So work can also be written as F into S cos theta. See, F into S cos theta or S into F cos theta, both W equal to Fs cos theta. For finding the angle between the two, questions may be coming. Cos theta equal to what? F dot S divided by W. W equal to Fs cos theta equal to W by Fs. W is F dot S. So cos theta equal to F dot S divided by Fs. And Fs is the product of moduli of F and S. So F dot S by Fs will give you cos theta and you can find out that angle. So this is most important one. So for finding work done, if force is mentioned as 3I minus 2J plus 4K and displacement is given as 2I minus 3J minus 4K, then what is the work done? Work done is equal to F dot S. That is F dot S. Why you take the dot product? You take product I dot I is 1. I cap dot I cap is 1. Dot product of orthogonal unit vectors I dot J 0. I dot K 0. J dot K 0. But I dot I 1. J dot J 1. K dot K 1. We know we have learned. So I dot I 1. So 3 into 2 6. Minus 2 into minus 3 plus 6. So 3 into 2 plus 6. Minus 2 into minus 3 plus 6. Plus 4 into minus 4 minus 16. Plus 4 into minus 4 minus 16. Then 6 plus 6 12 minus 16. So you get minus 4 joule. Given force is in Newton, given displacement in meter, then work done you will get in joule and this 4 joule. Why minus sign? Because that angle should be an obtuse one. Let us find out that angle. Cos theta is equal to F dot S by modulus of product Fs. F dot S is already known to you. What is F dot S? Minus 4 divided by. What is modulus of F? Modulus of F is equal to square root of 3 square plus minus 2 square is 2 square plus 4 square. What is modulus of displacement vector? Square root of 3 square plus 2 square plus 4 square. 3 square plus, so 3, 2, 4 here, 2, 3, 4, that's all. Both will be same. How much is this one? Square root of 9 plus 4 plus 16. That is 16 plus 9, 25. 25 plus 4, 29. You get root 29. That is square root of 29 is the modulus of displacement. Modulus of force is also same. Square root of 29. That is minus 4 divided by 29 is cos theta. So as cos theta is a negative figure, theta should be an obtuse one. Okay, this is the way by which you find the angle between two vectors. One, force and displacement. You can find work and also compute angle between force and displacement from the data. If force is perpendicular to displacement, F dot S will be 0. If force is perpendicular to displacement, their dot product is going to be 0. Orthogonal vectors, their dot product is 0. That concept is also very important, is tested in many of the competitive examinations. Okay, so work done by constant force you follow F dot S. Maybe the forces and displacements given in vector form, you can compute the work done like this, F dot S Fs cos theta. But if force is variable, you can make use of variable forces, work done by variable forces. Work done by net force appears as change in kinetic energy. Work done by conservative forces appeared as negative change of potential energy. Work done by non-conservative forces appeared as change of mechanical energy. By heart, all these standard results. That is all about work energy theorem. We have many applications based on that. You try to practice all that. Many solved exercises are also there in our textbook. Text-wise, let us proceed. All this we have discussed. See this one, angle between these two forces you can find out. Dot product as well as angle between the two. You can practice as we have done just before. Now, See this. Work energy theorem, we have an application here. And see that application question. Example 6.2. It is well known that a raindrop falls under influence of downward gravitational force and opposing resistive force. And that resistive force is proportional to the speed of the drop. We have learned already in chapter fluids from Stokes' law. A spherical droplet when falling through viscous medium, it assumes a terminal velocity. And because of a viscous force acting on it, which is given by Stokes' formula, 6 pi eta RV. And that viscous force, which is a resistive force, which is proportional to the speed. Consider a drop of mass 1 gram falling from height 1 kilometer, hits ground with a speed 50 meter per second. What is the work done by gravitational force? What is the work done by the unknown resistive force? Work done by gravitational force, work done by conservative force. Gravitational force is a conservative force. Conservative forces are those forces which have their own potential energies. സ്വന്തമായി പൊട്ടൻഷ്യൽ എനർജി ഉള്ള ഫോഴ്സുകളാണ് കൺസർവേറ്റീവ് ഫോഴ്സ്. ഗ്രാവിറ്റേഷണൽ ഫോഴ്സ് ഒരു പോപ്പുലർ എക്സാമ്പിളാണ്. കൺസർവേറ്റീവ് ഫോഴ്സിന് വർക്ക് ഡൺ, കൺസർവേറ്റീവ് ഫോഴ്സുകൾ ചെയ്യുന്ന വർക്ക് പാത്തിന് ഡിപ്പെൻഡ് ചെയ്യില്ല. Work done by conservative forces, they do not depend on the path followed. It only depends on initial position, final position. Friction is a non-conservative force because it is a path dependent. It does a path dependent work. Frictional forces does path independent work. Air resistance, viscous force, frictional forces, all are doing path dependent works. That's why frictional forces are non-conservative. Non-conservative forces, they do not have their own potential energy. So work done by non-conservative forces, that work cannot make any change in potential energy. But if a conservative force is doing work, that can change potential energy. Okay. Work done by conservative forces can decrease potential energy. How can you justify this? If a conservative force is doing a positive work, then definitely potential energy has come down. Let us justify using the more popular case, gravity. An object is taken from a height to a lower height. Their weight, which is the gravitational force acting vertically downward, displacement is also downward. So angle between force, weight, gravitational force, which is conservative. Angle between conservative force and displacement is 0. Angle between conservative force and displacement is 0. That means work done by conservative force is positive. So we say conservative force does positive work. Conservative force does positive work. As the vertical height decreased, potential energy, gravitational potential energy also has come down. That's why there is a popular saying, work done by conservative force has negative of change of potential energy. If conservative forces do positive work, potential energy reduces. But if conservative force does negative work in a given situation, then potential energy increases. When an object is lifted up from surface of earth, the lifting force is acting upward, conservative force is acting downward. Displacement is upward, conservative force is downward. Angle between force and displacement is 180. Then work done by gravity, work done by conservative force is negative. So see, conservative force has done negative work, so potential energy increased. Okay, normally things happen in a direction to decrease potential energy. What is the conclusion? If potential energy increases, something unnatural has happened. That's the philosophy of life also. From that we have many, this policeman used to prove many of the cases thinking like that. This has happened naturally. This is to happen naturally, but something unnatural has happened there. Some influence of some external agencies has happened there. That is why only it could have happened like this. That is their thought process. Water flows from higher height to lower height. Water tries to decrease its potential energy. Every beings, living being and non-living beings, tries to decrease potential energy. A tree when cut falls down to trying to decrease potential energy. A stone when dropped tries to decrease potential energy. Water flows down in the direction of decreasing potential energy. Current flows in the direction of decreasing voltage. Wind blows in the direction of decreasing pressure. Electric field is in the direction of decreasing potential. Like that, water flows in the direction of decreasing potential, decreasing height. താണ നിലത്തെ നീരോടു അങ്ങനെ ചൊല്ല് ഉണ്ട്, പ്രോവർബ് ഉണ്ട്. താണ നിലത്തെ നീരോടു, ചെരിഞ്ഞ സ്ഥലത്തേക്കേ വെള്ളം ഒഴുകുള്ളൂ, താഴേക്കേ വെള്ളം ഒഴുകുള്ളൂ. That's all about potential energy. Potential energy is of great importance. It's little bit tough also because potential energy depends on the reference plane, reference position. Myself may have positive potential energy with respect to one reference frame. Myself may have zero potential energy with respect to some other frame attached to myself. Myself may have a negative potential energy with respect to some other frame. So depends on frame of reference, but kinetic energy doesn't depend on frame. Kinetic energy can never be negative. Kinetic energy can be zero because when it is at rest, a body at rest has zero kinetic energy. But a body at rest can have a potential energy. Potential energy arises only because of configuration or position or state of strain. A spring, when unstretched, has no potential energy. But a stretched spring has a potential energy. A twisted wire has a potential energy. A ball at a height has a potential energy. So due to position, due to configuration, due to state of strain, potential energy arises. Potential energy has a conservative force. Potential energy can be a part of a conservative force. Force can be derived from potential energy. Conservative force can be derived from potential energy. All these things are very important while revision. You have to go through all these things qualitatively based on previous topics that we have learned during revision. Anyway, this is a revision time. You have already learned all the things. Then it is important to conclude making correlations among whatever we have learned in different chapters. Then only you can bravely answer statement type questions. See here. Work done by gravitational force is the change of potential energy. So that is mgh. What is mgh here? Mass into mass. Mass of the body. Mass of the body is 1 gram. So 1 into 10 power minus 3. G is taken 10. H is 1000. 1 kilometer means 1000 meter. So that 1000 and minus 3 cancels. So you get 10 joule. 10 joule is the gravitational potential energy change involved in this process. And that is only the consequence of work done by conservative force. So work done by gravitational force is positive here because force is in the downward direction. Displacement is also in the downward direction, mgh. But what is the work done by the unknown resistive force? From that height ball, the drop falls, what is the expected kinetic energy? That is half mv square. That is half mv square. That is 1.2 joule. Is the change in kinetic energy expected? As initial kinetic energy 0 starting from rest. Change in kinetic energy equal to the final kinetic energy. So final kinetic energy is only 1.25 joule, but initial potential energy was 10 joule. So 10 joule of that potential energy, out of which only 1.25 joule has been appeared as kinetic energy. It was expected entire 10 joule is to be appeared as kinetic energy. It doesn't happen. Why? Because of these frictional forces. So the rest of that energy is appeared as work done by resistive forces. So what is the work done by resistive forces? Difference, that is minus 8.75. Resistive forces do negative work. Viscous forces do negative work. Very important problem. The work done by non-conservative force is equal to change of mechanical energy. That can also be used for directly solving this problem. Now, work energy theorem, also this box is quite important. Erg means, that is also a popular unit of energy, 10 power minus 7 joule. Electron volt, very popular one, 1.6 into 10 power minus 19 joule. Calorie, 4.186 joule. Kilowatt hour, 3.6 megajoule. And watt hour, 3.6 kilojoule. A cyclist comes to a skidding stop in 10 centimeter. Their friction should be there. Then only there is a skidding stopping. The friction involved is sliding friction. Force on the cycle due to the road. Road exerts a force of 200 Newton over cyclist. What is the force on cyclist from the part of the road? Given 200 Newton. And we know Newton's third law. The force exerted by the road on the cycle is 200 Newton. Then force exerted by the cycle on the road also should be 200 Newton. Every forces, they appear in pairs. Action and reaction. The forces are equal and opposite. Then what is the work done by the cycle on the road? Work done by the cycle on the road. Work done by the cycle, see, work done by the cycle on the road is equal to force exerted by cycle on the road multiplied by displacement of the road multiplied by cos of the angle between the two. Here, what is the displacement of the road? The road is a stiff road, hard road. So that maybe a tar road. The road has not torn. Road has not chipped off. Road move ചെയ്തിട്ടില്ല, തെന്നിപ്പോയിട്ടില്ല. For road in a displacement 0. Displacement of road is 0. So work done by the force exerted by the cyclist on the road is to be 0. Because the point of application of the force is not moved. A force does a work only if the point of application of the force moves. A child pushes a wall tirelessly but fails to displace it. Displacement of the point of application of the force is 0, so work done by the child is 0. A force can do work only when the point of application of the force undergoes some displacement which is not perpendicular to the line of action of the force. Force in the line of action perpendicular അല്ലാത്ത രീതിയിൽ displacement ഉണ്ടെങ്കിൽ മാത്രമേ ആ ഫോഴ്സിന് വർക്ക് ചെയ്യാൻ കഴിയൂ. In same situation there may be several forces. Some forces are maybe doing positive works, some may be doing negative works, some may be doing zero works, all that. So here, what is the work done by the rod on the cycle? Vice versa, think. Work done by rod on cycle is equal to force exerted by rod on cycle multiplied by displacement of the cycle. See, definitely cycle has undergone a displacement of 10 meter. And cos of the angle between these two, cos of the angle between force exerted by cycle on the road, road on the cycle and displacement of cycle is 180 degree. Because road exerts a force, say towards east on cycle, but cycle displaces towards west. So angle is 180, so that work is negative. And cyclist displaces. So point of application of the force displaces, so work is not 0. What is that work? Force into displacement. Force is 200, displacement is 10, so 2000 joule is work with minus sign, minus 2000. So work done by cycle on the road is 0, but work done by road on cycle is minus 2000. Okay, so that Newton's third law like features are not there for works. Forces are equal and opposite, but works are not equal and opposite. Okay, works are not necessarily equal and opposite. So that solved example is very important. Every solved examples are to be learned clearly by heart it. Kinetic energy, that also is very important. Formula for kinetic energy. Formula for kinetic energy, everybody knows. Kinetic energy is equal to half mv square. Kinetic energy can also be written as p square by 2m, where p is the linear momentum. Kinetic energy proportional to square of the speed. Kinetic energy proportional to square of linear momentum. If momentum doubles, kinetic energy 4 times. Momentum tripled, kinetic energy 9 times. Momentum halved, kinetic energy 1/4. Momentum 1/3, kinetic energy 1/9. Like that. Momentum increased by 10%, kinetic energy increased by 21%. Momentum increased by 20%, kinetic energy increased by 44%. Momentum increases by 30%, kinetic energy increases by 69%. 30 into 2 plus 3 square. 60 plus 9, 69. Momentum increases by 40%. 40 into 2, 80. Okay, 80 plus 4 square. 80 plus 16, 96. Momentum increases by 50%. 50 into 200. 5 square 25. 100 plus 25, 125. So when momentum increases by 50%, its kinetic energy increases by 125%. But if momentum decreases by 50%, what happens to its kinetic energy? Also decreases by what percentage? There you subtract. 50 into 200. It was 100 plus 25 before when increased. It is to be 100 minus 25 when decreased. So 100 minus 25, 75. So when momentum increases by 50%, kinetic energy increases by 125%. But when momentum decreases by 50%, kinetic energy decreases by 75%. That's very important. Similar questions may be asked. Now, continuing. Kinetic energy. And this example, in a ballistic demonstration, a police officer fires a bullet of 50 gram, speed 200 meter per second. On a soft plywood of thickness 2 centimeter, bullet emerges with 10% of initial kinetic energy. What is the emergent speed of the bullet? So very simple substitution of that kinetic energy formula. Initial kinetic energy half m v initial square, that you can compute to get 1000 joule. 1000 joule. Now what is the final kinetic energy? Only 10% of initial kinetic energy it emerges. So final kinetic energy is 100. 10% of 1000. Then 10% of 1000 is 1000 into 10 by 100. That is 100. So emerging kinetic energy is 100 joule. What is the emerging speed? Half m v final square is 100. That's the final kinetic energy. So v final 63.2. So kinetic energy reduced by 90%. Kinetic energy reduced by 90%. Initial kinetic energy was 1000. Now it has become 100. That means it has reduced by 90%. And speed reduced by 68%. See that difference. That's very important solved exercise here. Work done by variable force, we can use that integral formula. If you have force displacement graph, care should be taken to find work done from force displacement graph. You find the area under the graph. That also very important question. Here you can use it. Force on y-axis, position on x-axis. Here, for the first 10 meter distance, graph given, force is of 100 Newton and is constant. Next 10 meter, further 10 meter, from 10 meter to 20 meter, force decreases from 100 to 50. Then what is the total work done? Force displacement graph, total work done is the area under the graph. Total work done is area under the graph. Here there can come many questions based on this graph. Here let us go through that. 100 Newton force over 10 Newton, then applied force reduces. Total distance through which the trunk has been moved is 20 meter. Plot the force applied by the woman and the frictional force, which is 50 Newton versus displacement. Calculate work done by the two forces over 20 meter. What is the force work done by the applied force? What is the work done by frictional force? Work done by frictional force will be, frictional force is constant. Kinetic friction does not depend on velocity. And 50 Newton is the force. Height is 50. What is the breadth? 20. So 50 into 20, 1000 minus 1000 will be the work done by the frictional force over the entire journey. Minus 1000. Work done by frictional force over the entire journey is minus 1000. Now, what is the work done by the minus 1000? What is the applied force does what work? For getting, you find the work area under this graph. Area under this graph. Area of this rectangle plus area of this triangle plus rectangle. Or you can make use of area of that, area of a trapezium plus area of that rectangle. Then you will get the total work done. Because that work is positive also. Now let us move on to another exercise based on a variable force problem, which is a position dependent one. Block of mass 1 kilogram, horizontal speed, initial speed 2 meter per second, enters a rough patch ranging from 0.1 to 2.01 meter. Retarding force is acting on it. Retarding force varies with position minus k by x, where k is some constant. K is given 0.5. And that is 0.1 to 2.01 meter. You can follow this rule for force. Final kinetic energy and speed. Final kinetic energy equal to initial kinetic energy plus work done by that force. And that force is minus k by x, so that is a retarding force. Then final kinetic energy equal to initial kinetic energy is half m v initial square. Half m into v initial is 2. Half into mass is 1. Half into 1 into 2 square. That is 2 joule. So initial kinetic energy is 2 joule. Initial kinetic energy 2 joule plus integral 0.1 to 2.01 minus k by x dx. That minus carries here as the work done is negative. Minus carries here. K constant. 1 by x dx integrate when you get log x between the limits 0.1 and 2.01. So half mv square, which is 2, minus k log 2.01 by 0.1. That is 20.1. 2 minus log 20.1. You can find it out as 0.5 multiplied by 0.5 minus 1.5. And you get 0.5. So final velocity equal to 1 meter per second. So here we have used work energy theorem for variable forces. Like this, every solved examples you can practice. All this we have discussed. Concept of potential energy we have discussed. A conservative force has its own potential energy. Every conservative forces can be expressed as a negative gradient of potential energy. Conservative forces can be expressed as negative gradient of potential energy. Potential energy decreases steeply in the direction of conservative forces. Potential energy decreases steeply in the direction of conservative forces. Conservation of mechanical energy. What do you mean by that, conservation of mechanical energy? In the absence of any non-conservative forces, that means frictional forces do not do any work. Only conservative forces do work. Then total mechanical energy happens to be a constant. Means mechanical energy is the sum of kinetic energy and potential energy. So kinetic energy plus potential energy is a constant throughout that process. For example, when a ball is dropped from a tower from rest, initially the ball is at rest. Now its potential energy is maximum. At rest, kinetic energy is zero. So mechanical energy is equal to its potential energy at all. Falling down, when it reaches the base, reaches the bottom, reaches the ground, we assume ground as the reference line. Potential energy needs a reference line. So potential energy of that small ball at the surface of that ground is zero, but its potential energy has been completely converted into kinetic energy. So total mechanical energy on the ground is kinetic energy. On the way, potential energy and kinetic energy are not zero. So total energy is partially kinetic and partially potential. There also, sum of kinetic energy and potential energy is a constant that is equal to the potential energy at the beginning, that is equal to the kinetic energy at the bottom. Water falls from a reservoir. So mgh is the potential energy of m kilogram of water from h meter height. Okay, that potential energy completely converts into kinetic energy, and that kinetic energy, some part of that potential energy is used in heating that amount of water. Some part of that energy is used in producing sound. Okay, if ice falls from some height, some part of potential energy of that mass of ice is used for changing the state of ice, for melting. Some part may be used for increasing temperature of that ice if ice was at a negative temperature initially. In all such cases, we use conservation of mechanical energy, conservation of energy. In the absence of non-conservative forces, mechanical energy is a constant. Mechanical energy is sum of kinetic energy and potential energy. And that is exemplified in vertical circle. Vertical circle is a very important exercise. What do you mean by vertical circle? When a bob is allowed to undergo a circular motion in vertical plane, driven by gravity alone, assume there is no friction. There should be certain critical minimum speed which it should possess when it is at the bottom. Then there will be some speed, some critical characteristics, some critical speed, minimum speed, which it should possess when it is at the top and every positions. Then only it will continue. If there is no friction, it will be a perpetual one. It will continue. For example, a string at the end of which is torn, you try to oscillate it like this freely. Then you increase the speed when it passes through the mean position. Increase the speed at the bottom. At certain speed, it will just go once around. Okay. Throughout that course of the vertical circle, if the string remains at the same radial distance, radius of that circle bounded by that stone is a constant, then that is called a vertical circle. That can be possible even with more speed, greater speeds. But it is possible critically with a minimum speed at the base, which is root 5 GL. Root 5 GL. So speed possessed by it at the bottom is root 5 GL, where L is the length of the string. When it reaches the top, its speed will be root GL. then the body is set to execute vertical circle with critical speed or looping the loop, loops the loop. All this can be understood with the help of mechanical energy conservation. Everywhere at the top, at the bottom, when it is horizontal, where its speed is root 3gl, everywhere you try to find out the total mechanical energy, that is a constant. Okay, assuming the line passing through, horizontal line passing through A happens to be the reference line. Potential energy there is 0. Potential plus kinetic is equal to total. Potential 0. Kinetic half m v square. V square is 5gl. So you get 5 by 2 mgl as the total mechanical energy. When it is at the horizontal line, its potential energy is mgl because L is the vertical height. Kinetic energy is half into m into speed square is 3gl. You get 1 plus 3 by 2, still 5 by 2 mgl. When it is at the top, what is the kinetic energy? Half m into root gl square, that is half mgl, plus potential energy is 2 mgl. So 2 plus 2 mgl plus half mgl is 2 into 2, 4, 4 plus 1, 5, still 5 by 2 mgl. So everywhere total mechanical energy is 5 by 2 mgl. But kinetic and potential energies, they adjust internally. But total remains a constant. This is true only in the absence of non-conservative forces or in the absence of work done by non-conservative forces. Non-conservative forces may be present there, but they may be inactive. In such situations where there are numerous number of forces acting on a system, but non-conservative forces do not perform any work, only conservative forces perform work. So total mechanical energy is a constant. Repeating conclusively, vertical circle looping the loop with critical speed. Speed necessarily followed at the bottom is root 5gl, at the top it is root gl, at the position where the string remains horizontal is root 3gl. Okay, you can try to find out the tension when it is at the bottom. Tension during vertical circle, tension at the bottom. Tension at the bottom. When the bob is at the bottom, what is the tension? Tension T is equal to mg plus mv square by L. mv square by L is the centrifugal force which is acting radially outward. Tension is acting radially inward. At this position A, at A, what is the tension? T is equal to mg plus mva square by L. So TA equal to mg plus m by L into va square is 5gl, root to 5gl is va. That is TA equal to 5 mgl plus mg, L gets cancelled. 5 mg plus mg, that is 6 mg. So what is the tension at A? Tension at A is 6 mg. Then when it reaches the point B, at B let us do the same. At B, when it reaches the point B, the bob is now at the top. What are the forces acting on? Tension is acting always away from the mass. Now the mass is at the top at B. Tension is down. Mg is also down, but radially outward centrifugal force is upward. Then balancing at B. Vb square by L is equal to T plus mg. That is T at B is equal to mvb square by L minus mg. That is m by L into Vb square. Vb is root gl, its square is gl, minus mg. L gets cancelled. Mg minus mg becomes 0. So the tension happens to be minimum when it reaches the top, and that is 0. So for maintaining vertical circle, the minimum tension over the entire circle is 0. Tension cannot be negative. The maximum tension is what? 6 mg over this critical circle. Okay. It doesn't mean that the tension, maximum tension cannot be more than 6 mg. It may be more than 6 mg, it may be 7 mg. Maximum tension happens at the bottom. It may be 7 mg, but the minimum tension there will be mg. The difference of the tensions at the bottom and top is 6 mg. That's true. That is only because of conservation of energy. 6 mg is at the bottom, top it is 0. If 7 mg at the bottom, top is mg. 8 mg at the bottom, top is 2 mg. So 2 mg and 8 mg difference is 6 mg. So difference of tensions at the bottom and top is always 6 mg. If it follows vertical circle driven by gravity. Vertical circle driven by gravity. The difference in tensions bottom and top is 6 mg. Okay, that's all about conservation of mechanical energy. Looping the loop, vertical circle, that part is very important. Now, during oscillation, how to apply the energy conservation? During oscillation, a pendulum when oscillates, it is possessing two energies simultaneously. Can possess two energies, one kinetic and the other potential. Kinetic plus potential energy is a constant. At the extreme position, it has only potential energy, no kinetic energy. At the mean position, its potential energy is minimum. That can be zero. Minimum potential energy can be zero, not necessarily. So the maximum kinetic energy is equal to the maximum potential energy. That is the energy conservation. Maximum kinetic energy equals maximum potential energy. So V maximum is the maximum speed possessed by the oscillating body when it passes through the mean position, given by root of K by M into Xm, where K is the force constant. The force, spring force F is equal to minus Kx. Hooke's law, it obeys Hooke's law. Spring has a potential energy U is equal to half K x square. Spring force is also conservative. The spring potential energy can also be written as half F into X. One more expression, F square by 2K. All these three forms of potential energy of a stretched spring are important. Spring force is equal to minus Kx. So all these illustrations are important. You go through them. Now the important topic of this chapter is nothing but collisions. Before that we have power. Let me conclude with power and collisions. Power. Power is the rate of doing work. Power P is equal to dW by dt. Power is equal to rate of doing work. Joule per second, or watt is the unit. Horsepower is the unit of what? Horsepower. 1 horsepower is 746 watts. That is the unit of power. That's a commercial unit. Electrical energy has a commercial unit that is called electrical energy, kilowatt hour. 1 kilowatt hour is 1 unit of electricity by this KSCB. 1 kilowatt hour means 3.6 megajoule and 1 watt hour is 3.6 kilojoule that we have discussed so far. So power is the rate of change of work, rate of energy, dW by dt, rate of change of kinetic energy, rate of change of potential energy, rate of energy, rate of change of total mechanical energy. All this can come depending upon the situation. If kinetic energy has not changed, only potential energy changes. So power is the rate of change of potential energy. If kinetic energy also changes, then total power is the total rate of change of kinetic energy and potential energy. So rate of change of mechanical energy will be the total power. Now we have to move with collisions. That part is much more important. Conservation of energy, all that we have discussed. Now the topic collisions is more important. Collision. See? Different types of collisions we have to go through. First one. Perfectly inelastic collision. Let us discuss perfectly inelastic collision is that collision in which colliding bodies move together or stick together. Both the colliding bodies or whatever number of colliding bodies will move together after collision. That is called perfectly inelastic collision. In perfectly inelastic collision, if the first body is of mass m1, first body moves with the speed u1, second body, say at rest 0, so u2 equal to 0, second body is at rest. That is the total momentum before collision. Momentum is to be conserved in every collisions, because in collisions forces involved are only internal, no external forces in any collisions. So in whatever collisions, total momentum before is equal to total momentum after. It is not momentum of individual particles, but total momentum is going to be conserved. So total momentum before collision for first body and second body, that is equal to total momentum afterwards. But here one thing is to be noted: in perfectly inelastic collision, colliding bodies move together gaining a common velocity. So total mass is to be clubbed together because both are having a common velocity. So V is equal to m1 u1 by m1 plus m2 is the formula for the common velocity of the bodies together moving after collision, which is perfectly inelastic. In this process, there some kinetic energy will be lost. The lost kinetic energy delta K can be found by finding the final kinetic energy minus initial kinetic energy. Final kinetic energy is less, so energy is lost, you get delta K negative. I am writing its numerical value. Half m1 m2 divided by m1 plus m2 into u1 minus u2 the whole square. If u2 is 0, you can easily simplify it because u2 is 0. So that is the lost energy and common speed in perfectly inelastic collision. Now coefficient of restitution. Restitution coefficient. Coefficient of restitution, let us use this E. It is defined as the velocity of separation. Separation divided by velocity of approach. Velocity of separation divided by velocity of approach is the coefficient of restitution. Coefficient of restitution is defined as the ratio of velocity of separation and velocity of approach. And the general formula can be V2 minus V1 divided by U1 minus U2. Or you can also write V2 minus V1 by U2 minus U1 with a minus sign. Okay, for perfectly inelastic collision, V1 is equal to V2. V1 is equal to V2, that is perfectly inelastic collision. So V2 minus V1 becomes 0. So coefficient becomes 0. So if restitution coefficient is 0, such a collision is called perfectly inelastic collision, in which colliding bodies stick together after collision or move together after collision. A mud blob thrown onto wall and mud blob sticks together. That collision is perfectly inelastic. In this collision, maximum percentage of kinetic energy is lost. Okay, here non-conservative forces are present. That's why some energy is lost. Some of the potential energy is lost. Second type of collision is perfectly elastic collision. Perfectly elastic. In perfectly elastic collision, restitution coefficient is going to be 1. What do you mean by that? That is V2 minus V1 is equal to U1 minus U2. This is important. That is V21 equal to U12. What do you mean by that? Relative velocity, if collision is in one dimension, it's very simply explained. Relative velocity of second body with respect to first body equal to relative velocity of first body with respect to second body. If relative velocities bear a ratio numerically 1, then such a collision is called perfectly elastic. In this process also momentum is conserved. We assume that second body is at rest for all such collisions because that is only mainly discussed in our syllabus. M1 U1 equal to m1 v1 plus m2 v2. In this process, kinetic energy is also conserved before and after the collision is over. But we have seen before in perfectly inelastic collision, in completely plastic collision, kinetic energy lost. So in perfectly inelastic collision, kinetic energy is not conserved before and after. But in perfectly elastic collision, kinetic energy is conserved before and after the collision is over. So kinetic energy before is half m1 u1 square, that is equal to kinetic energy after is half m1 v1 square plus half m2 v2 square. Like this, only there are these two formulae in solving all this. Solving these two formulae, we can conclude. We have all deduced this formula. I am not trying to do that in quick revision. V1 is equal to m1 minus m2 by m1 plus m2 into u1, and v2 is 2m1 u1 divided by m1 plus m2, because second body is at rest. These two formulae can be used for finding velocities of first body and second body after perfectly elastic collisions in one dimension. If the collision is one dimensionally, restitution coefficient can be defined as relative velocity after collision divided by relative velocity before collision. And this formula v1 and v2 also important. v1 equal to m1 minus m2 by m1 plus m2 into u1. v2 equal to 2m1 u1 by m1 plus m2. All this important. If m1 equal to m2, m2 much greater than m1, all that to be discussed. See, if m1 equal to m2, very important result comes out. m1 equal to m2, v1 equal to u1. Sorry, v1 equal to 0. First body comes to rest because second body was at rest. So velocity of first body becomes velocity of second body after collision, and velocity of second body becomes velocity of the first body after collision. That means in perfectly elastic collisions in one dimension, of identical bodies, they exchange their velocities. So they exchange their momentum. They exchange their velocities, and also they exchange their linear momentum. That is called momentum exchanger or velocity exchanger. Only used when the two bodies are identical. Two bodies are identical. Also, collision should be one dimensional. Also, the collision should be perfectly elastic. Now, if collision is inelastic, the third possibility, inelastic. What is the possibility? Restitution coefficient is less than 1. There kinetic energy before and after not conserved, but momentum before and after is conserved. Momentum conservation is valid for every types of collisions before and after and also in between. But kinetic energy conservation is not valid during the collision duration. That means during the time of impact, during the short time of impact, kinetic energy is not conserved. But for only perfectly elastic collisions, kinetic energy before is equal to kinetic energy after. So kinetic energy conservation is valid only for perfectly elastic collisions before and after. It is inelastic collision, restitution coefficient less than 1. So relative velocity finally less than relative velocity initially, all that important. The fourth possibility is superelastic collisions. Superelastic collisions mean what? E greater than 1. That means after collision, kinetic energy increases in all explosions. Kinetic energy of the fragments will be greater, much larger than the kinetic energy of the parent. A bomb at rest, kinetic energy 0, but explodes into fragments. You add kinetic energies of all those fragments, you get a huge value. So kinetic energy has increased much. From where does that kinetic energy increase? Internal energy converted into kinetic energy in perfect superelastic collisions where restitution coefficient finds a value greater than 1. Okay. Now, if the collision is two-dimensional, if collision is two-dimensional, First body of mass m1 moving with speed u1 collides with second body of mass m2 which is at rest. Now after collision, the first body m1 may be taking a path like this with a speed v1. Second body may be mass m2 taking a path this one, velocity v2, and this angle theta 1, this angle theta 2. Here also we can use if collision is perfectly elastic, that if E is equal to 1, collision is perfectly elastic, kinetic energy before equal to kinetic energy after. So half m1 u1 square equal to half m1 v1 square plus half m2 v2 square. Momentum conservation. m1 u1 is equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2. As momentum is a vector, we have to resolve. Similarly, that is only horizontal components I have equated. Vertical component of initial momentum is 0. That is equal to m1 v1 sin theta 1 plus m2 v2 sin theta 2. So you can make use of these three equations in solving problems. Also, if collision is like this, two-dimensional, also called oblique collisions, and also it is elastic only in our syllabus. Elastic oblique collisions. If masses are identical, that's very important. If m1 is equal to m2, if m1 is equal to m2, that means masses are identical, restitution coefficient is 1, collision is oblique. Oblique. So oblique elastic collision of identical masses. Theta 1 plus theta 2 is equal to 90 degree, it can be proved. Theta 1 plus theta 2 is equal to 90 degree. So oblique elastic collisions, the angle of scattering, that is theta 1 plus theta 2, which is equal to theta, that is complementary. Theta equal to theta 1 plus theta 2. If theta 1 is 30, theta 2 is 60. 30 plus 60, 90. Okay, angle of divergence will be 90. So their velocities will be at right angles. If one is 20, the other is 70, so and so. So that is also worth noted. So we have discussed different types of collisions, repeating. First one, perfectly inelastic. Colliding bodies move together, stick together. Second, perfectly elastic. Third one, inelastic. First one, restitution coefficient 0. Second one, restitution coefficient 1. Third one, restitution coefficient inelastic less than 1. If E greater than 1, that is super elastic. In super elastic collision, restitution coefficient is greater than 1. Different types of collisions, every collision's momentum is conserved, but kinetic energy need not be conserved before and after. In only one collision, kinetic energy before equal to that after, and that is what collision? Elastic collisions. But during collision process, kinetic energy is not even conserved for elastic collision also. Okay, in this chapter we have discussed work, energy, power and collisions. Major portion is conservative forces, potential energy changes, all that. Work energy theorem. It's very important. Work energy theorem. Stick on to work energy theorem. Most of the question papers we used to see questions from this chapter, particularly Neet and all, one or two questions, sometimes two questions. Earlier 3 questions were asked from this chapter. Nowadays 1 or 2 questions asked. Okay, mains we used to see many questions in different papers. One paper mains question, one question only used to see from this chapter. Vertical circle and all are important. Okay, last 2 years, 22 and 23, these questions from vertical circle were not seen, but questions from collisions are seen. Okay, with that we wind up with the quick revision of chapter work, power, energy. We'll be soon meeting with the next chapter, rotational dynamics. Till then, bye. Thank you.